Hello, I'm Joshua Brakensiek, and I'm presenting our work, Smooth Complexity of Two-Player Nash Equilibria. This is joint work with Shant Boodaghians, Samuel Hopkins, and Aviad Rubinstein. Before we jump into the main result, let's take a moment to pause and reflect. Take a deep breath, close your eyes, and think back about your career. If it weren't for people like Cook, Levin, and Karp, pioneers of theoretical computer science, how much time would you have spent looking for polynomial time algorithms for NP-hard problems? What we're going to ask today is, what's an exciting area in algorithms for which we don't know of that many limitations? That would be smooth analysis. At a big picture, we're going to be bridging two different areas, smooth analysis and algorithmic game theory, in an important problem at their intersection known as smooth Nash. In the process of investigating this problem, we'll be looking at just the tip of the iceberg of I think, a very important area called smooth complexity. Going forward in this talk, we'll first start with a discussion of smooth analysis, then we'll jump into actually discussing Nash equilibria. Then we'll give an overview of our proof as well as a more detailed analysis, and then we'll go into future directions of our work. The most important case study for smooth analysis is the simplex algorithm for linear programming. The simplex algorithm has been known for decades to work very well in practice, but there are certain instances on which it takes exponential time, such as the Klee-Minty cube. Spielman and Tang showed that these hard instances, however, are not robust. In fact, if you just add a little bit of random noise, the hard instances become easy. The important question, though, of this talk is, when does smoothed analysis not apply? This leads to the three worlds of smoothed complexity. Smoothed Algorithmica, where smoothed analysis applies. Hardness of Approximation, where you can't even approximate. And smooth complexity, where you can approximate, but smoothed algorithms do not exist. For smoothed Algorithmica, problems in algorithms can be solved via smoothed analysis. In particular, if you look at this picture, we have an instance x, and then we have some ball of radius sigma, which represents possible deviations of the problem. In particular, in blue are the points which are easy, and notice that they are very numerous. The hard points are isolated. Examples of algorithms and problems with this behavior include the simplex algorithm, the k-means algorithm, the knapsack problem, and very recently, the local max cut problem. In contrast, hardness of approximation, every point in the neighborhood of an instance is hard. As you can see from the diagram, there are no blue points. There are numerous examples of this, including k-means problem, max set, and the traveling salesman, all of which are due to the innovations in the PCP firm from the 90s. As middle ground, we have smoothed complexity. This is an instance where there are easy points nearby in blue, but the vast majority of points are hard. In particular, the hard points are robust. We aren't aware of too many examples of this. In this talk, we'll talk about the smooth Nash problem as an example. As an open question to those who are watching this on YouTube, what are other examples of the smooth complexity problem? Leave a comment if you happen to have a suggestion of an interesting problem which also falls under smooth complexity. And these are the three worlds: smooth algorithmica, smooth complexity, hardness of approximation. As we mentioned, there are many cases of hardness of approximation, many examples of smooth analysis, but smooth smooth complexity, so far we only know of Nash. Now that we've discussed smooth analysis and smooth complexity, let's move on to discussing Nash equilibria. We start by defining a Nash equilibrium. In our context, we'll have a two-player bimatrix game. In this case, there are two players, Alice and Bob, both of whom have a set of strategies. Alice, in this case, has 3 strategies, and Bob also has 3 strategies. Alice will pick a row I, and Bob will pick a column J. And the reward will be the respective entries of their payoff matrices. For instance, if Alice picks the second row and Bob picks the second column, Alice will get a payoff of -1 and Bob will get a payoff of 1. Note that this game depicted is a zero-sum game, which will be important later in the analysis. Formally, we'll have two matrices A and B in R to the n by n, and we can assume the strategy entries are bounded between -1 and 1. This is just normalization. Alice will pick strategies x and y in R to the n, whose entries sum to 1. So for instance, they're both picking probability distributions. Alice's payoff is x transpose AY, and Bob's payoff is x transpose BY, just the expected value of their strategies. We say that they're in equilibrium if neither benefits from changing their strategy. So formally, that means the payoff Alice gets x transpose AY is at least as good as any strategy EI she could play, assuming Bob's strategy is fixed. Likewise, for Bob, x transpose BY is at least x transpose BEJ for all j and n. And a very important theorem due to Nash, foundation of much of economics and game theory, is that Nash equilibrium always exists. Sadly, it's hard to compute an equilibrium in general. This is known as PPAD completeness, and it's the analog of NP completeness for what are known as total functions, because there's always an answer. It's not like something like set, where you might have an answer and might not have an answer. An important theorem in this space, probably the most important theorem in this space, is that computing a Nash equilibrium in a two-player bimatrix game is PPAD complete. In case you haven't heard of PPAD before, its canonical problem end of a line is like how SAT is the canonical problem for NP completeness. In this, you have an exponential sized graph, which is a circuit. Each vertex has at most one edge going out and at most one edge going in. And you have circuits to query for each vertex what goes out of it and what goes into it. Your problem is to have a special vertex 0, which has no edges coming into it, and thus there must be some other vertex by parity that also doesn't have any edges coming out of it. And your goal is to find some endpoint of a line. This is known as the end of a line problem. Other PPAD complete problems include Brouwer's fixed point theorem and Sperner's lemma. Returning back to Nash, recall the important theorem that computing a Nash equilibrium in a two-player bimatrix game is PPAD complete. In fact, these offers show a stronger statement. It is PPAD hard to find a 1/Polyn approximate equilibrium. What does that mean? Well, an approximate equilibrium is one in which neither player benefits from changing their strategy by more than epsilon. So in particular, there's no individual strategy that has more than an epsilon bigger payoff than what's in the equilibrium. Note that this rolls out a smooth algorithm for 1/Polyn noise. So in particular, this means that Nash equilibrium is not like linear programming in that you can smooth the problem a little bit to make it easy. Let's now discuss some algorithms for finding Nash equilibria. One example is linear programming, but this is rather fragile as it only works for zero-sum games, where a is equal to -b. There is a generalization of this called Lemke-Hausen, which is a simplex-like algorithm, but it takes exponential time in the worst case. In some sense, this is really begging for a Spielman-Tang type smoothed analysis, but one hasn't been found. Another important algorithm, the LMM algorithm, what it does is it finds an epsilon approximate equilibrium by guessing and checking a 1 over epsilon sparse epsilon net of strategies. Basically, you just discretize each probability in the strategy to a multiple of epsilon, and then you brute force over all these possibilities. This finds an epsilon approximate equilibrium in quasi-polynomial time, and a simple modification of this algorithm actually finds an equilibrium in a random game with high probability. Here, a random game means that the entries of A and B are drawn from some distribution, such as uniform or Gaussian. So it's not even smooth, because smooth is everything has, you're adding a little bit of noise to some given data, whereas here it's like everything's zero. You're adding noise to the all zeros matrix. An important result by Rubinstein showed that LMM is essentially tight for epsilon approximate Nash equilibrium, assuming the ETH, the exponential time hypothesis, for PPAD. Note that this does imply some smooth lower bound because of the approximate hardness, but in fact you can get a much larger hardness for the smoothed problem. Okay, so now let's get into defining smooth Nash, because we haven't done that yet. So we're going to have some payoff matrices A and B, and we're going to let A epsilon, B epsilon, B, n by n matrices sampled IID uniform on minus epsilon epsilon. We're going to have our epsilon smooth Nash algorithm be finding an equilibrium A plus epsilon, B, B plus epsilon. In particular, we're going to just say uniform noise in this talk, but similar results hold for any distribution with sufficiently bounded support. Our main theorem is that there is a universal constant epsilon naught more than 0, such that epsilon naught smooth Nash is PPAD complete. This strongly refutes conjectures of Smealman-Tang from 2006 and Chin-Deng-Tang from 2009. And it rules out general smooth analysis of Lemke-Hausen and LMM. Now that we've explained what smooth Nash is, let's jump into the proof overview. In our proof, the high-level idea is we're going to reduce from epsilon smooth Nash to a 1 over poly n approximate Nash problem. And the way we're going to do this is to wash out the added noise so that the hard game to which we added the noise shines through. The first key tool in this reduction is what is known as padding. So here we have two payoff matrices for Alice and Bob, and what we're going to do is we're going to make many copies of each strategy, as shown in these pictures, so that instead of just having one version of each strategy, we'll have many different copies. I only have two versions of each due to space, but there will actually be many, many more copies. This will make it so that when you add the noise, we will hopefully concentrate over the many different strategies. Just doing padding is not enough to wash out the noise, because if you have many different copies of a strategy, there'll be many different kinds of noise being added to all those copies, and we can just extract out the most extreme one and cherry pick it to find an equilibrium to our problem. So in fact, we're in some sense worse off by just doing padding. To get around this, we need to use the following theorem of Jonasson and Roberts, which says that with high probability, the unique equilibrium in a random zero-sum game has omega n support. So in particular, in a zero-sum game, the strategies really like to be spread out. We'll use this as a gadget in our reduction so that we'll end up causing the independent noise to cancel out. And in fact, the zero-sum noise will just happen to cancel out as well, as you'll see, which is enough to have the hard game shine through. So now let's just jump into the full reduction. We're going to take some hard to approximate game P and Q. We're going to pick n equal n to the 100. We're going to sample some z. we're going to set A to be P tensor J plus Z plus A epsilon, and B is going to be Q tensor J minus Z plus B epsilon. And the idea is any equilibrium of AB corresponds to a 1 over Pollyann approximate equilibrium of PQ. Okay, if we have something like this, remember we said that finding a 1 over Pollyann approximate equilibrium is hard, will be done. Okay, so now let's jump into a more detailed analysis. Okay, we will now perform the analysis in 3 steps. Recall we use the notation xy for the equilibrium of A and B. For our first step, we'll show that with high probability, all of these equilibria have large support, as in polynomially large support. In our second step, we'll show that with high probability, all x and y have small 2 norm. This will be important for concentration, as just having large support won't be enough. Finally, we'll show that with high probability, for all these equilibrium, the noise will wash out. In particular, the noise terms, z plus a epsilon and minus z plus b epsilon, their effect on the payoff is negligible, n to the minus omega 1. Combining these steps, this will show that xy is a 1 over Pollyann approximate equilibrium of p and q tensored with j, and then we can just project out the repeated strategies to get an approximate equilibrium of p and q, which we said was hard. This will finish the proof. Before we discuss the proofs of the 3 steps, let's first say some important facts about Nash equilibria. The first fact is for almost any A and B, and for every support S and T, there's at most one equilibrium xy with those given supports. And further, S and T have to be the same size if there's any. This will allow for a union bound, as instead of looking over the continuous space of all possible strategies, we can just discretely look at each possible support S and T and enumerate over those. Another important fact is that if x and y are an equilibrium of A and B, then for any strategies I and j in the support of x and y respectively, the value of playing that strategy is equal to the value of the equilibrium. X transpose AY is equal to EI transpose AY, and X transpose BY is equal to XBEJ transpose. And the reason why this is true is rather simple, as the value of the game has to be at least the value of each of the individual strategies. But we're averaging over these strategies, so they have to be equal. This will be important, as it will imply that a lot of strategies have to have the same values, which means our random variables are going to need to have lots of correlation. This will be our in particular concentration. This will be important later on. Let's start with the proof of large support. That is, with high probability, all strategies x and y have polynomially large support. For this talk, we'll just give the proof of Jonathan for zero-sum games. The proof in general is very similar. So let's take a union bound over the supports of x and y. Notice that 0 is equal to x transpose A plus by, because it's a zero-sum game, is at least EI transpose AY plus X transpose BEJ for all I and J. But if I is not in S and J is not in T, this can only happen with probability 1/2 just because of random choices. Thus, there's only an exponentially small chance this S and T will actually work. And because of that, the union bound implies large support with high probability. The full proof is very similar. You just find a large zero-sum-like game within A and B. Now that we've shown with high probability all the strategies have large support, we'd now like to show that they have small 2 norm. This will allow us later on to show that the random noise washes out. In order to prove this, what we're basically trying to rule out is strategies which put a lot of mass on just, say, like a small number of strategies, say putting 80% of the mass on a single strategy. To rule this out, we're going to use the fact that the payoffs of all the different strategies in your support are the same. All the EI transpose AYs are the same. So to do this, we'll take a union bound on the support of X and the support of Y, as before. And the intuition is if the 2 norm of Y is big, most of Y's mass is on a sparse collection of coordinates. What we show is that for any sparse vector, the distribution of strategies, these payoffs, EI transpose AZ for a sparse vector Z, are going to anti-concentrate. They're going to be very different with high probability. In particular, what this means is even if we throw back in the dense part of Y, so we take this sparse part of Y, throw back in the dense part, it's not enough to fix it, even if it's working in your favor. As such, we can then say, by contradiction, that the 2 norm of Y has to be small, and also the 2 norm of X. For the final step, we want to show that everything concentrates. Now that we know that X and Y have small norms, we want to show that when you apply the noise to these vectors, you actually get small values. And the way you do this is it suffices to show that a particular random matrix M has the following inequality, that if you take X transpose My divided by the 1 norms of X and Y, it has at most square root of log n value for all xy of unit norm. So we're taking this over the entire unit spheres for both x and y. And the way you prove this is by showing that you have what's known as a sub-Gaussian process, and as such, you can apply an inequality due to Talleyrand. This shows the concentration we need. So to recap, we have that for any equilibrium x and y of A and B, all the equilibrium have large support, they have small 2 norm, and thus the noise washes out. As such, our equilibrium of our smooth game is actually an equilibrium of this P tensor J, Q tensor J game, which, once we project out, is also an equilibrium of P and Q. Since P and Q, finding an approximate equilibrium is hard, finding a smoothed equilibrium of our A and B is also hard, QED. Now that we have given the proof analysis, let's now wrap up. Our main result is that finding a 2-player equilibria to a smooth game is just as hard in the sense of PPAD completeness as the original problem. A key insight is that this cannot be derived by hardness of approximation alone, as the approximation problem has a quasi-polynomial time algorithm. Thus, this is a concrete instance of smooth complexity. Important future questions include, what about super-constant smooth Nash? All we've shown is that there exists a constant for which smooth Nash is hard. We didn't say anything about their existing algorithms once you go past the constant. Is that still PPAD hard? What about Lemke-Hausen for zero-sum games? Can we do smooth analysis of that? We have some experimental evidence even that shows that this is likely the case. It'd be cool if this could be worked out. Another thing to think about is, what are other examples of smooth complexity? Is there a more general theory to be found? I would definitely like to know. And thank you everyone for taking the time to watch this.